And now our next speaker, Daniel Martí, will speak about defensive programming techniques in Go. Please welcome Daniel Martí. He'll speak remotely.
Thank you. So my name is Daniel, and I work full-time on the Q language. I can hear myself in the echo. Can I stop that? Apologies. Okay, that should be fine. So like I said, my name is Daniel. I work full-time on the Q language, which is written in Go itself, and I'm going to be talking about defensive programming techniques in Go. So defensive programming is defined as a way to ensure the continuing function of a piece of software under unforeseen circumstances. What that means is that you write your Go code today, it works fine, but what if in the future people use it in weird ways, or it gets weird input, you don't want it to blow up, or you don't want it to do something weird and end up in a bad state. So as an introduction, Go as a language is safe. That's something that's said quite often. So for example, as long as you don't use unsafe, the language already defends us sometimes, most of the time. For instance, you don't have to worry about memory safety. You don't have to worry about buffer overflows, or you can have nil pointer dereferences, but since you cannot do pointer arithmetic, you cannot get, for example, bad pointers that point to memory that you don't own, stuff like that. And the type system in general also helps, as long as you're careful with the empty interface, which can point to any type. So that's the only part that might be a little bit tricky. However, there's still plenty of room for defensive programming techniques. Go is still a pretty simple language, so there's still plenty of room for mistakes. So we'll start with a few simple examples. The first example I want to show is a switch. So here we've got a main program that takes one argument and essentially does something depending on what this argument is. So if we go look at this code now, and we run it, go run. So first off, if we run it with no arguments, it panics because it expects exactly one argument. If we run it with one or two, it does what we expect. But if we run it with some other argument, it does nothing, which is also a bit weird. So something you can do is add a default case. And then here maybe we do println unknown argument. So in this case, it will still do something that is going to be more helpful to the user. And this is a very simple example, but this is just to get us going on understanding what defensive programming is. So in general, you do want to add default cases to pretty much most or all of your switches, because if you're not, there should be a good reason why you're not, right? And in general, it's better to be safe than sorry. And this is especially relevant when you're handling enums. So for example, enums in Go are integer types that have iota values, right? But at any point in the future, your code base might gain a new enum value, a new iota line. So if such a new value appears, you want your various pieces of code that switch over those enum values to start failing in some helpful way. If they start silently doing something that's wrong, that could cause bugs in production. And this also applies to type switches. So for example, if you have a type switch over an empty interface, in general, you should have a default case and then decide what should the default case do. It could do something like show an error or maybe have a default behavior. Another example is cases, APIs that return error, but you're fairly sure that that error should never happen. So here's an example, and I'm going to pause on this code for 20 seconds or so, because what this code is trying to do is it creates a new buffer with the string foo and a new line. It copies that buffer's contents to standard output, and then it asks the buffer, hey, please unread the last byte that was read. So in this case, you would expect this should be the new line, right? And then print what's left inside the buffer. And this code doesn't check any of the errors, because a reasonable person would say, well, copying to standard output, this shouldn't fail. And if it fails, something went horribly wrong anyway. And unreading the last byte of the buffer should also be fine, because I literally just read from it. So it should be fine. There's nothing fancy going on here. So let's look at our code here. So this is the same code that I just showed you, but in a runnable way. So if we run it as expected, the first thing that it does is it copies the standard output. It copies the buffer to standard output, and you can see that there, the foo is right there. But then the unread byte ends up being empty. So the buffer after we unread one byte is still empty. So something went wrong here. And we're not seeing what went wrong because we're ignoring errors. So let's go out of our way. And the simplest thing you can do is panicking if anything goes wrong and saying, shouldn't happen. This is the laziest way to deal with this, right? A proper program would probably have better error handling, but because this is just a sample main program, let's just panic if an error that we think shouldn't happen happens. So if we run it, the copy worked fine. So the first error was nil, but the second error was non-nil. So unread byte, previous operation was not a successful read. So that is the reason why our unread left us with no bytes instead of 1 byte. So if you think an error is impossible, you should still panic in the case that it occurs, because if your reasoning is wrong, or for any reason the API breaks in the future, or any other unforeseen circumstance, you might get silent breakage, which I reckon is probably the worst kind of breakage. A loud breakage might be annoying to the user, but at least it's easy to debug and figure out what's going on. So in this case, what went wrong is that so in this case, ignoring the error from printing to standard output, like we said, is fine. But the problem was that in unread byte, the documentation, I believe, says it unreads 1 byte from the last read call. But io.copy, because it reads in a loop, the last read call just ran into end of file and didn't read any bytes. So unread byte in this case is failing because there's no byte to unread. The last read call didn't read anything. And this is a little bit weird, but it's one example of these errors that you think might never happen, but actually can happen in practice. So the next example I want to show is shadowing. So shadowing in Go is, for example, let's look at this example. We've got a function that takes an empty interface as a parameter v, and then we do a type switch. So if it's an integer, we want to print that integer converted to a string. And if it's a string, we want to quote that string and then print that string in its quoted form. So that seems fine. Let's go look at the code again. So again, it's the same. It's just that our main function now calls this function with 1, 2, 3, and foo. So let's run it. And the integer case works, but the string case does something weird. And let's look at the code again. The reason is that we've got 2 variables here, right? We've got the v of type interface, and we've got the x. That's the variable in the type switch. So x will either be an integer or a string. But we made a typo. We made a mistake. When we println in the string case, we used v instead of x. And the compiler is happy with this because it doesn't violate any of the type system's invariants. So for example, x is used. So x is used here. V is used, and it's in scope. And println takes empty interfaces as parameters. So this is also fine. So nothing in here in terms of the type system is wrong. But of course, our program is incorrect. So we could fix it. We could change this to be an x. And then this will do what you expect. It prints the quoted version of foo. But the possibility of making this typo is still there. So the way I would write this code is shadowing. So instead of saying I declare a new variable x, I'm going to shadow v with a new v. So let's replace all x's with v. And what this ends up doing is that inside the scope of the switch, there's only 1 variable now instead of 2. I'm shadowing the empty interface v with the typed v. And it's basically impossible for me to pick the wrong one because there's just 1 here, right? And if we run this, you can see it works perfectly fine. So the way the spec defines this is that an identifier declared in a block may be redeclared in an inner block or a nested block. You can think of it that way. While the identifier of the inner declaration is in scope, it denotes the entity declared by the inner declaration. I'm not a big fan of the second sentence. It's a bit convoluted, but essentially it's saying that in our example before, the V that you see here is the V that was declared in the inner block. So this line, not this line. Another way to look at this is that you've got two blocks. You've got the block with the scope of the function body itself in light blue, and it declares one variable in that scope. That's the V in the parameter. And then the inner block is the type switch, and it also declares one variable, the V as well. But because it's an inner block, it's shadowing. It's temporarily replacing the outer V. So like we said, shadowing can avoid mistakes because it reduces the amount of names in scope. And I'm a human, I make mistakes. The more options I have, the higher the chances that I'm going to pick the wrong option, right? So here's another example. When you look at the GoAST package, which is a syntax tree of Go source code, you have nodes that contain other nodes, right? So in this case, you have a function that takes an expression, and if that expression is a composite literal, it wants to range over the sub-expressions inside that composite literal. And I did this in a way that shadows twice. And this works perfectly fine if you only need one expression at a time, because it only keeps one expression in scope. So there's no chance of you using, for example, the parent expression when you meant the inner expression, right? So if you shadow, as long as you don't need to use two expressions at once, I think it's quite nice. It might not be the best in terms of good naming, but I think in terms of defensive programming, I think it can be a good thing. One caveat is that this doesn't work with function parameters, which I'm actually quite sad about. So in this case, we've got a visit function that takes an AST node again, and then I want to type assert it into a composite literal. And then I want to use that typed node, which is no longer an interface, and access one of its fields. And this fails. And it fails because the scope, there's just one scope here. If we ignore the if not okay scope that's nested there. So the node parameter is declared in the function body scope, but the second node that we declare is also in the same scope. So there can be no shadowing because there's no inner scope. We don't have a switch here, for example. So like we said before, we've got one scope and then declaring the same variable twice in the same scope. And the reason for this is because the spec says the scope of an identifier denoting a method receiver, function parameter, or result variable, in our case a parameter, is the function body. So there's just one scope. Another example, which could tie into our previous example, is that you can use nested scopes. You can just insert them anywhere you want. So in this case, imagine that I want to have a temporary buffer to do some operation, like, for example, fill the debug variable with some bytes. But I want to make sure that this buffer is only used within these 3 lines of code, and it doesn't get used later for something else that I'm not anticipating. So I could just insert a block here and then do my thing. And when I close the block, the buffer is no longer in scope. The buffer has no chance of being misused. I would say that this in general is not necessary, but if you have particularly tricky code where using a variable after its lifetime is a problem, or you have a high chance of making mistakes because there's lots of names in scope, I would say this can be a good way of reducing the chances of mistakes. Another example is invariants. So here we've got a function that picks a number of names at random from a list. So you give it a slice of names, which is a slice of string, and then a number integer. And then it loops over that number, picks a random name, and prints each random name. So let's go look at that. So we've got the same function here. And then we call it we've got a list of 4 names. So first we pick 3 names at random from that list of 4 names. Then we print 0 names at random from that list. And then we print 3 names from an empty list. So these are edge cases that you might not have thought of initially when you wrote this API. So if we run it, you can see that Picking 3 names from the list works fine. Picking 0 names from the list also works fine because our code will essentially never enter the loop. But picking 3 names from an ill list will panic. And the reason for that is because we will enter the loop, we will pick a random number between 0 and 0, that is 0, and then we will try to index into names. But getting the 0th element of an empty list is essentially a panic, right? Because that list has no elements. You cannot take the first element of an empty list. So that panics. So what we could do here to be defensive is have some invariants. So we could say, if length of names equals 0, then we panic saying the names list cannot be empty. And we could also say if number equals 0, we also panic saying it doesn't make sense to pick 0 names. If the user really wanted to pick 0 names, they wouldn't be calling the API in any case. It doesn't panic, but if we're being defensive, it's a choice you could make. And then we could have a bit of GoDoc for the human. So we could say pick at random, picks a number, a random number of names from a list. And then we can have 2 invariants. We can say names must not be empty. Number must be a positive integer. So when somebody looks at this GoDoc, they understand those invariants, even though they're just in plain English, and then they are implemented in the code. So if I run the code again, you can see that trying to take 0 names panics, like as we said, and then if we comment that out and run again, then the other invariant is broken. So if we comment that out, then we can see our program does what we expect. And this is more of a philosophical choice. You can choose how aggressive your invariant should be, but I would argue that at least this invariant should be in place, because if it's not there and that input comes in, then you're going to panic anyway. So like we said, if you have invariants that you want to enforce, you should document them in your GoDoc and assert them with panics. And I would say that the bare minimum is that you should have invariants for any inputs that would break your code. In this case, for example, a panic. So another example that I want to talk about is struct embedding. And this is possibly the trickiest example, so I'm going to go a bit slower. But if any of you struggle to follow, because we will post the recording and the slides later, you can always go through these slides at your own pace whenever you want. So here we've got a struct that embeds a pointer to big int. And as a reminder, big int is the big package in the Go standard library implements arbitrary precision integers. So in this case, big int is an integer that can be as large as you want. It can encode, 10 quadrillion, and it's fine. It's not constrained by, for example, 32 or 64 bits of word sizes on your machine. And big int implements encoding JSON methods, such as unmarshal JSON, because when you encode and decode JSON with big ints, you want it to encode as the big integer, right? So if you've got 10 quadrillion, you want it to encode as the digit 1 and then a large number of zeros. You don't want it to encode in the memory layout, which is a struct with some fields. But what if we want to override that unmarshal JSON method? So in this case, we've got a struct that embeds big int. I called it embedder because I think that might be the right way to call it, but it's a slightly weird name. And then what this method does, it's something a bit silly. It just prints, hey, I'm here, I was called. It allocates the big int because it's otherwise a nil pointer that would panic. And then it calls that integer's unmarshal JSON. So let's look at the code. So the code that I just showed you is this first bit. So let's just run that for now. And you can see the type here. So what the code does is it unmarshals the bytes 1, 2, 3, which are valid JSON. It's a JSON number, into a value of type embedder. And we essentially just panic if something goes wrong, and then let's see. So we can see that our unmarshal JSON was called, our println was called. And what about a slightly more contrived case? What if we define a new type, a new name type, and I'm calling it new embedder just to differentiate it, and its underlying type is embedder, and then I try to do the same with new embedder. So what would happen then? And the answer is a panic, which is very unfortunate. But you can see that embedder, like we said, works fine. New embedder panics. And the reason is an invalid memory address or nil pointer dereference. And you can see that what happened is that from encoding JSON, we went straight into calling mathbig unmarshal JSON. We skipped over our unmarshal JSON method, which would have allocated the integer, right? So in this case, because nothing allocated the integer, we got a nil pointer dereference because this big int is nil, and then trying to initialize it just panics. Now, the reason why this happens is a bit tricky. The reason why this happens is because a type definition creates a new distinct type with the same underlying type and operations as the given type and binds an identifier, the type name, to it. So in this case, when we declare a new embedder type, we are creating a new name type whose underlying type is the same underlying type as embedder. And what this means is that it's the equivalent of saying type new embedder struct embeds bigint, but it ignores the method on embedder. And the reason is because the method is attached on embedder as a named type and not on its underlying type. And I realize I might have lost half the audience at this point. So essentially what I'm saying is that when you declare a new name type, you're ignoring all the methods of a name type that you're reusing. And that is the gist of it. So that is why our example panics, because we're ignoring our method. So struct embedding can be useful, but overriding a method can be quote unquote skipped over, even if by mistake, if you fall into this trap. So there is an upstream issue about this. It's 41685. And it is sort of a known problem, like you could call it a food gun with struct embedding. And there are two workarounds proposed. One is a vet check. So you can think of a static analysis that tells you if you do type new named embedder, for example, it would say, hey, vet could say, the method new named.unmarshal JSON refers to the embedded int.unmarshal JSON, not embedder.unmarshal JSON. So this kind of static analysis could warn you, hey, by the way, this is doing something that you might not expect. It could be argued whether or not this would be a false positive, because maybe you want to do that, but I struggle to imagine why anybody would want to do this. It feels like a very weird edge case. Another workaround, which is maybe the proper defensive programming solution, is to prevent the food gun by adding an extra type layer. So in this case, imagine that we have a type called embeddee that we want to override. So instead of embedding it directly to override its method, we have another type in the middle, which is called private embedder. And it's important that this type is private because only you can use it. And this one does the embedding and the overriding. And then your exposed type embeds the private embedder. And this works because if somebody does type new embedder, like we said before, they get the underlying type of struct embedding private embedder. And private embedder is still there in this case. So private embedder still overrides the method. So in this case, because our exposed type doesn't have any methods directly on itself, this food gun is removed for any API users. So I have the solution down here. So let's look at it. So we have a safe embedder that instead of embedding bigint directly embeds private embedder. And let's call this private embedder. And then private embedder embeds bigint. So what happens if I use safe embedder? So now they both do what you would expect. It is a bit unfortunate that you have to go through this extra step of having an extra type. And I would argue this is the reason why the issue that I mentioned before is still open, but it's also one of those language features that has a rough edge, and smoothing it out might be tricky. So until that happens, if you ever use struct embedding in exposed types, I would say be mindful of this and maybe add the defensive programming workaround to make sure your users don't have unforeseen breakages. The last example that I want to go over is validity lifetimes. So here's an example. Imagine that you have an API that converts integers to strings. So if you give it 1, 2, 3 as an integer, it's going to give you the bytes 1, 2, 3, the string 1, 2, 3. It's going to convert it into a base 10 string integer. So you can do that with string conf.i2a or format int, but that allocates every time you call it, right? So in this case, our API, what it does is it has a buffer and it reuses that buffer for every call. So you don't allocate for every single call. But because it reuses the buffers, when you make one call to i2a in this API, the next call to i2a will overwrite the previous value. So one result is only valid until the next call. And one way we can make the API less prone to misuse is that instead of returning the bytes, it calls a callback function that has access to those bytes. So it's like a view, a temporary view over that result. So let's look at lifetime. So we've got the same code that I just showed you. And then we ask it, please convert 1, 2, 3, and 4, 5, 6 to strings. And then we just print those strings. And we can see, we'll run 6. We can see that this works fine. But what if we're a naughty user and we use those bytes later than we should, after they are meant to be used? So in this case, we have a kept variable where we keep those bytes for longer than we should, and we ask it to convert 1, 1, 2, 2, 3, 4, 4, 4. But then the view function keeps those bytes in the kept function, and then we say, these are the bytes we kept shortly after, before we called i2a again. And then we do the same after another call to i2a. So we want to look at what our kept bytes look like after a couple of calls. So kept shortly after, the bytes are still valid, technically, because there has been no other call to i2a. But after the second call to i2a, you can see that 987 has replaced part of the digits of our first number. So you can still see 2, 3, 3, 4, 4, but then 987 has corrupted that number. And the reason for that corruption is because I'm keeping those bytes for longer than I should. So I already used the API with the view function as a way to try to prevent this, but the user can still do whatever they want, right? So one way to further decrease the chances of this misuse is to explicitly corrupt the bytes after each call to the view callback has finished. So in this case, we could do c.reuse buffer. We could say that the first byte will be a question mark. So now we can see that proper use of the API shows you the proper digits, but if you keep those bytes for longer than you should, then the bytes are corrupted. And this is still broken behavior, but if I was looking at a program behaving like this, I might think that nothing is going wrong. But if I see a program behaving like this, the question mark is going to tell me that something wrong happened, and then I'm going to investigate where I went wrong, and hopefully I would find that I'm breaking the contract of this API. So essentially, if a value should no longer be valid for use, I would say making its contents explicitly invalid, even though it might be a slightly inefficient or user non-friendly thing to do, it will help prevent bugs in some edge cases that might be tricky to debug. So now I've shown you 6 examples, and I want to briefly talk about what we could automate in each one of those. So the first one was a switch. You could possibly enforce default switch cases when switching over enum-like types, and I believe some static analysis tools already do this. I would say in most cases this makes sense. In a few cases, it might find false positives, cases where there's no bug, even there couldn't be any bug. So I think that's the reason why this is not widespread. But I would like to see some form of this happen more widely. Another one is the case where API calls never error, and we ignore the error. And there is a tool called errorcheck that complains about all ignored errors, but I think that's going too far because some errors are documented to always be nil. So, for example, if you read from a bytes buffer, that read call should never should only give you a nil error or an EOF error. So any other error is basically impossible, right? So in that case, ignoring the error is fine because you're just following the documentation. But error check would still yell at you. So something that sits in between would be nice, but I'm not sure if it can be automated. In the case of shadowing, enforcing this feels harsh because at the end of the day, it's a matter of personal preference and style. I would say that there should be some form of automation to tell you when your scopes have too many names in them. So for example, if I'm developing some code and I'm in a deeply nested block and there's like 50 names in scope, I personally struggle to maintain or understand that code because there's just so many names in scope that I'm just, I can't keep track of that many names in my head. So I would say that that should be something that a linter should flag. But again, that limit is gonna depend on each project and person. What about invariants? There are some languages that have pseudocode that has logic expressions that allow you to define invariants that are actually enforced and checked. We could potentially do this in Go docs. So you could imagine like a Go expression that must be true or something like that. But I also don't imagine this would fit Go as a language because it would feel like kind of over-engineered to have something like this inside Go comments, inside Go docs. I still think some automation would be nice, but I think it would probably have to be outside of Go as a tool chain, maybe as a separate tool. In terms of struct embedding, this one is tricky. I think the spec could be clear to flag this foot gun, and a vet check would be nice, like I showed before. And I think the spec could also show the trick that is using an extra type in between to prevent the foot gun. I don't think we can change the way embedding works, because if we did that, I think too many Go programs would break, because embedding is just used. It's not a super popular feature, but it is used quite often. So I think changing the semantics of when it carries over methods and things like that, I think it would break too many programs. And what about lifetimes? This one depends on each API, because each API defines its own lifetimes. But I think it could be a recommended pattern. I've seen it be used in, I think the protobuf library uses this in a couple of places. So I think this could become more of a recommended pattern, especially because Go is garbage collected, but at the same time, for the sake of avoiding allocations, we tend to reuse memory in some cases. And as a final example without code, I'm gonna talk about Harem's law. And Harem's law is essentially saying, with a sufficient number of users of an API, it does not matter what you promise in the contract. All observable behaviors of your system will be depended on by somebody. Essentially, what this is saying is your users will depend on every single aspect of your API over a long period of time, even if some of those aspects are undocumented. So, and the tricky thing is that you can have a Go API that has some undocumented behavior, which behaves in a mostly deterministic way, and then people start depending on it. And then if you break it, if you change that undocumented behavior in the future, you technically can do that because it was undocumented, but you may suddenly be breaking a lot of users whose programs were working fine for years because that behavior was mostly deterministic. So it can be argued that that's a breaking change, and that's happened in the JSON package like too many times at this point. So any internal detail that we didn't document properly, people started depending on it. And then if we want to change it to, for example, improve the default behavior or improve performance, then 10 users come yelling, "You broke me," and it's hard to argue that they're wrong because their Go code has been running fine for years. And yes, they didn't read the docs properly, but it's a decision on whether you want to put your users first or your code first. And Go in general, at least the standard library, puts the users first. So one defensive solution is to randomize those undocumented behaviors or undocumented features if you think they might be prone to this issue. So here's an example. Maps in Go are not ordered or sorted. So when you range over them, the spec says that that order of iteration is unspecified. It's not guaranteed. So what the main Go compiler and implementation does is that whenever you range over a map, it randomizes the order of the iteration. So this essentially allows you to change, for example, the implementation of maps in the Go runtime, because even if another map implementation would store the keys in slightly different ways, because the order of iteration is always randomized, in theory, no program should have been working for years and then suddenly break, because the behavior before and after is in both cases, it's randomized. Another example is that when you run Go test, it runs your test functions in lexical order. So for example, test foo would run after test bar because the B comes before the F. So this can allow for side effects to creep in. So you could, for example, have a case where test foo only passes because it depends on some global state left behind by test bar. And you might never notice unless you do something like run test foo on its own without anything else. One way to prevent this kind of issue is in your CI, you can use go test shuffle. And shuffle essentially it randomizes the order of the tests being run. So it helps catch this kind of unforeseen dependency between tests. Another one that's not fixed per se, it's an ongoing foot gun, you could say, is that the sort package has an unstable sort API. So it has sort.stable, which is stable, and then it has sort.sort, which is unstable. And what this means is that if you're sorting a slice of elements and two elements are considered to be equal, the relative order of those two elements in the resulting slice is undefined because it's an unstable sort. And the advantage of unstable over stable is that it's faster. It can be faster because it has to do less work. And Go 119 changed this unstable sorting algorithm. And the proposal, which was accepted and implemented for Go 119, said, the new algorithm is still an unstable sorting algorithm. It may rearrange equal elements differently compared to the original sorting algorithm in the sort package. So the proposal was already saying, we might break some users, but this was all documented. It was documented to be undefined. And the proposal is technically right, but a few projects and programs, including a couple of mine, broke because of this. And I think the solution would be, hopefully, for the unstable sort to randomize its sorting of equal elements. And you might not want to do that by default, but because that would be extra calls to, for example, compare between two elements, and that could be a regression in terms of performance. But you can think of alternatives like maybe only randomize if it's a test binary, even though I don't like that option that much. Another option could be only randomize if we built with the race detector on, because the race detector already randomizes some other things. You could think of an environment variable to turn it on, the randomizing. Or you could do it by default, and then you would surely break quite a few users like 119 did, but then you wouldn't break anybody ever again. So I think any of those options is better than not doing anything. So hopefully something will happen. And that is it for me. Like I said, I'm on Twitter as well, and that's my email as well. So if anybody has any questions, I believe we'll take some now, but I'm always reachable on Twitter if anybody wants to follow up. And thank you.
I wanted to just mention that anytime someone's taking responsibilities that feel like garbage collection, what you said with the like mess with the first byte is not a bad idea, and that's one of the things that Rust does, which is their co-located conference here. They do with their WebAssembly garbage collector. Effectively, when it goes out of scope, they muddle with the first bytes because you can tell, and they don't do that, for example, in TinyGo. So it's much harder to find a problem where someone's using memory after they should. So yeah, that was my comment.
Yeah, nothing to add. I think it's a worthwhile thing to do as long as it's cheap. I probably wouldn't do it if it makes the API 5 times as slow, but in general, that's not the case.
We have a question from a remote speaker now. Remote attendee, sorry. I'm gonna read it. So what about public Go APIs? Adding defensive programming to them could be a breaking change, no?
Yeah, and that's a tricky decision. I think that falls into, I think I had a slide about breaking changes as well. I think that falls into what your compatibility promise is. If your compatibility promise is that anybody who doesn't follow your documentation is on their own, then in theory, adding defensive programming is fine, because even if you break undefined behavior, it's fine for you. I would say that if any code wants to be as backwards compatible as Go itself, you should probably be somewhere in the middle. So if you're breaking users that are doing stuff that they shouldn't be doing, but there are too many of them that are getting broken, I would say that's a breaking change. So I think it depends on a case-by-case basis.
Okay, then if there are no more questions, thank you again, Daniel.
Happy to be here. Enjoy the conference.